This function over here is clearly singular at the origin because of this 1 over z here. The question is, what is the residue at the origin? So pause the video to try and calculate that residue based on a series expansion. So what is a series expansion? Well, if we write down z cosine 1 over z, thanks to Euler's, we can write this cosine as exponential j, and then the argument of our cosine, 1 over z, plus exponential minus j over z divided by 2. And now we have two exponentials, and we know what the series expansion of a complex exponential is, right? So we can write this as z over 2. And then for the first series expansion, we have a sum n going from 0 to infinity of the argument of our exponential, which is j divided by z to the power of n divided by n factorial. And then we have a second summation where we basically have exactly the same, but with a minus j. So minus j over z to the power of n divided by n factorial. By the way, here we're taking the sum of two series expansions. In this case, there's no harm in using exactly the same summation index. Things become different, of course, when you take the product of two series expansions. Okay, we have the Laurent series in a slightly messy form here. We're not caring about the whole Laurent series. We're only caring about the coefficient of 1 over z to get the residue. Now, when do we get 1 over z in these summations here? Now, because of the fact that we already have a z over here, we need to have an n equal to 2 to end up with 1 over z in total. So we only need to look at the coefficients that we have when we have the summation index equal to 2. In that case, we have 1/2, that's the 1/2 here in front. And then we look at what happens when we replace n with 2 here. So we end up with j squared divided by 2 factorial plus minus j squared divided by 2 factorial. 2 factorial is of course 2, so combined with the half we already had, that's 1 over 4. J squared is minus 1, minus j squared is also minus 1. So at the end of the day, we end up with minus 1/2 as the residue at the origin for this particular function.